recording. I am recording it the OBS, and I should record it with let me see, start recording. Okay, so last time we talked, we said that for the interactive processes, how are we going to know how long they are going to take to using the CPU, how we're going to make this decision. So this was the idea. We said that we would look at history, right? The history would tell us how long it worked the first time and the second time, and for the third time I can make a guess, and this is my guess. After I make the guess, I let the process run for a while, and I see how much it is taking, how long it's taking, and that becomes my T2. But before I guess T3, I know the value of T2, so I would multiply T2 with this value and multiply T1 and T0 that way. So every time I make a new guess, I would multiply the previous one with the value of alpha, and then I would add, let's say, T3 times 1 minus alpha. Okay, so this is how I make this calculation, shortest process next. So remember what we are doing here. We are trying to okay, let me go back a little bit. Let's see. Okay, so we are looking at scheduling in interactive systems. Okay, we said that interactive systems are a little bit different from the batch systems. That's what we know. With the interactive systems, of course, CPU utilization, system balance is important, but the most important thing is the interactivity. We should never lose the interactivity. On top of that one, after the interactivity, of course, this is a computer. I have to do lots of system related stuff. I need to do that too. So under these conditions, what kind of scheduling algorithm should I have? The first one was round robin. You remember round robin? It is very simple, very fair. But sometimes they say that this is too fair, because I like some of my processes to be prioritized. They have higher priorities. So how am I going to reflect those priorities? It's the priority scheduling. It says that I'm going to run the high priority tasks first. When I don't have any high priority task, I will run the next level priority. And they came up with these multiple queues. Each priority class has their own queue, and I run a round robin in each queue. And then we said that maybe okay, these are all okay, these are all fine. How about using this idea, shortest process next? Because when I do the shortest process next, that means that those are the, remember, we try to give priority to the IO bound processes, because they spend most of their time waiting for some IO. So as soon as they are ready to run, they should be run so that they can issue their next IO request. So shortest process next is the scheduling algorithm that I can use maybe with the scheduling algorithms, okay, as the priority. That's what we were doing, shortest process process next. And but the problem with the interactive task is that I don't know how long it's going to take. Okay, so this is a way to guess how long it's going to take for this task to be blocked. Okay, so that's what we do. Okay, another scheduling algorithm which could be used in combination with any other interactive scheduling mechanisms is the guaranteed scheduling. It is this. Let's say I have n processes. Okay, there are n processes. So that means that each one should use 1 over n of the CPU time. Okay, so each one should use 1 over n of the CPU time. That's no problem. So after each process runs, okay, before the operating system makes a switch from one process to another process, it calculates how much time it has used. Okay, so it says that process number 1, okay, it has a quantum of 100 milliseconds, but it used 50 milliseconds of it. Process number 2, it has a quantum of 100 milliseconds and it used 100 milliseconds. Process number 3, of course, it has the same amount of quantum time and it used maybe 20 milliseconds. So that means that I should give more priority to this P1 and P3, maybe more priority to P3 because it did not use the proper amount of the CPU time. So what would I do? I would say that this would be the priority. It's like 5. This would be the priority 1, and this would be the priority 2. So the highest priority would be P3, then P1, and then P2. So this way, I would say that I am guaranteeing the same CPU time for each process. Okay. So of course the scheduler has to make these decisions, and scheduler has to make these kind of calculations when you do the switching. Okay, any questions so far? Okay, then let's continue in that case if there are no questions. Another interesting idea, by the way, I think the book talks about maybe 5, 6, 7 different types of interactive processes, interactive scheduling methods, but in reality there are many of them. These are just representative ones, and I think the book has just collected interesting ones, or the simple enough ones. And one of them is the lottery scheduling. It's like buying a lottery ticket. Let's say I have P1, P2, P3, and P4, 4 processes. Okay, and I have, let's say, 100 lottery tickets. Okay, I have 100 lottery tickets. It's like Milli Piyango bileti, lottery tickets. So I will distribute these lottery tickets to these processes. Let's say the priorities of these of these processes are, let's say this is the highest priority. Okay, this is the same priority. This one and this one. Maybe let's make it this way. Maybe let's say this is 5 and this is maybe 3. This one is 3, okay, and this one is 1, and this one is 1. Okay, so what I do is I distribute lottery tickets. I distribute the lottery tickets to these processes. I have total of 100, so I give this guy 50 tickets. This one has 30 tickets. This one has 10, and this one has 10. Okay. When the time comes to scheduling, okay, at scheduling time, I would pick a random ticket between 0 to 99. Okay. So this one has the best chance of winning the lottery. This one has the second chance. These have the smallest chance of winning the lottery, but still they have a chance, right? So that means that I am kind of implementing the priority scheduling using this idea. The nice thing about this one is everybody has a chance to run. Everybody has a chance to get the CPU, but this one has a better chance of getting the CPU. Okay, and of course, as processes run, they get to exchange their tickets between themselves. such as client and server, such as client and the server. The server says that I am important. Server says that I should have the more priority, but for now, I don't have anything to do, so I am going to give my tickets to my client. You could do that. Okay. So Yasin is here. So Yasin is coming like 15 minutes late to the class, and he says hello. Okay, hello Yasin. Then. Okay, so that means that in the online world of teaching, we have this kind of coming in and going. Okay. Okay, Ahmed has a question. Is the scheduling method harder to maintain than the others? No, actually, it is very simple because you don't have to keep the priority queues, right? So all you need to do is you have a limited number of tickets and you need to distribute it. And distribution is done at the beginning of the process creation time, and during the scheduling time, all you need to do is just pick a random ticket, just take a random number. Okay, so this is not harder. This is simpler. This is simpler, and many solutions to problems like the priority queues and that kind of stuff. And as I said before, this one doesn't say that as long as P1 can run, it will run. It doesn't say that. P1 has the highest chance of getting the CPU. Still, P4 can use the CPU, but it's not going to be as frequent as P1. Okay, good. So let me move on then. Another idea is fair share scheduling. Okay. In some systems, interactive systems, time-share systems, the processes don't compute, but users do. Okay, this is my one large mainframe computer, and I have 1, 2, and 3 users using the computer at the same time. Okay, so things would not be that complicated if each one has a single process. Single process. But what happens if this third user has 1, 2, 3 processes? These two have a single process each. So that's not fair. So fair share scheduling says that fair share scheduling says that let's make this decision, okay, based on how much each user use the CPU, okay? Because if this user makes lots of processes, we don't want to encourage them forking just to get larger share of the CPU, okay? So we make our decision based on the CPU consumption of the users instead of process CPU consumption. Okay, of course, this person could have more priority than this person, or this person can have lower priority than this person. This could be still implemented, but I do my scheduling based on the user CPU consumption data. Okay, so that's called fair share scheduling. Okay, Yasin has a number. A number of tickets does increase or decrease after the selection, or the selection chance always the same. Well, this one, no, the number of tickets is always the same. The total number of tickets is always the same, and if the priorities of the processes do not change, then each process holds the same amount of tickets. But as this one says, tickets can be exchanged between the processes depending on the situation. Okay, so the one process might say that I am not going to be busy. I can be at lower priority, so I am going to give my tickets to my client because I know that the client is going to do lots of stuff. So if the picture is like this, their chances of getting the lottery is the same. So what happens if I add a new process, let's say P process number 5. Okay, I gave it to 10 tickets, so it's a lower priority. That means that this one will have a less because now I have a total of 110 tickets now. Okay, so this one has a lower priority now, but still it has the highest priority. Okay, we talked about this. So the last part is, let's talk about these real-time systems. So far we have looked at the batch systems, okay, and we looked at the interactive systems. Now we are going to look at the real-time systems. For the batch systems, CPU utilization, throughput, turnaround time, these were the things. For the interactive systems, it was the interactivity, quantum time, okay, preemption, that was the important thing. For the real-time systems, it is the deadlines, okay. Deadlines are the most important, and predictability, okay, kind of the side effect of deadlines. Users must know when their request will finish, okay. So it requires a very careful engineering of matching priorities to actual completion times and available resources. Okay, so usually, as I said before, real-time systems are not general operating systems. They are very specialized. Their processes are specially designed for the real-time systems. So the process knows that it is sharing the CPU with some other processes, and it should behave in a certain way. It cannot take the CPU forever. Okay, it has to finish its job in a given amount of time to meet the deadline. Okay, so the classical idea of preemption is not in the real-time systems. Real-time systems are not preemptive in the sense that we know, but they have their own kind of preemption. Each process is designed to be run in a certain amount of time, so you don't need any preemption. You cannot have a process in real-time systems to take the CPU and use it for a very long time. This cannot happen in the real-time systems because, as I said before, ordinary users are not allowed to run their programs on real-time systems. Okay, and usually these are embedded systems, sometimes very specialized systems, and operating system is designed along with the processes that run on the real-time systems. So meeting the deadlines is important. So that means that, let's say I have process number 1, process number 2, process number 3, process number 4. Okay, this one says that when I run, I will take 50 milliseconds. Okay, P2 says when I run, I will take 30 milliseconds. P3 says, okay, when I run, I will take 10 milliseconds. And this one says, when I run, I will take maybe 40 milliseconds. So how many processes can I add to this system without violating this rule, meeting the deadline? Okay, without going out of that rule. How many of them can I add more? Because each one is guaranteeing that I will not take more than 50 milliseconds. And this one says that I'm not going to take more than 30 milliseconds. That means that can I add as many as possible? No, the answer is of course no. There is a limit, and how do I calculate that limit? This is what we do. Okay. Remember this. Okay, so this says what? Oh, okay, duplicate, edit. Okay, I think I will do it. I will do it again. Process number 1 takes, I don't remember how long it takes. I think it takes 50 milliseconds. Okay, process number 1 . My pen is acting again. So the real-time systems say that each process should guarantee how long it's going to take, but also each process should have some kind of an idea, the period of the process itself. Process 1 might say that I will take 50 milliseconds to run, but I will run every 300 milliseconds. Process 2 might say I will take maybe 30 milliseconds to run, but this will happen every 500 milliseconds. So process number 3 might say I will take 10 milliseconds to run, but this will happen only in maybe 20 milliseconds. So it looks like process 3 is using lots of CPU time, although it says that I will be very, very quick. Okay. So how do I know that all three can be run on this system? So this is what you do. You add all these numbers: 50 over 300, 30 over 500, 10 over 20. Let's make this 200, okay? So that they are compatible. 10 over 200, and each, if all the additions of them is less than 1.0, less than or equal to 1.0, that means that the system can work in real time. Okay, so this is how you calculate it. We never had such a calculation in any other scheduling algorithms. Why? Because we didn't have these kind of deadlines. We never said that it's going to take 50 milliseconds every 300 milliseconds, and etc. For real-time systems, this should work. Of course, we should be careful about the process switch overhead too. Okay, so this is how you calculate if all the processes that you plan to run on your system is runnable. Usually we pick this, like maybe instead of 1.0, maybe we pick this much, 0.8, so that our CPU is always 20% free idle, just in case one of the processes takes a little bit longer, because there might be some bugs, there might be some other situations. So just to be safe, that all the deadlines are met with this kind of load factor. Okay, any questions so far? Okay, I skipped something here. Real-time systems. These are the two definitions related to real-time systems. People usually use these concepts. What did he say? Meeting the deadlines is the most important thing. If you miss the deadline, then you are dead. Okay, that's called hard real-time. So there are absolute deadlines that must be met. Otherwise, your real-time system is not a feasible real-time system. I cannot call the real-time system. It is a serious bug. Sometimes, for some cases, this is too strict. You might say that, okay, I like this feature, but this is too much. Maybe I can be like once in a while, maybe once in an hour, maybe once in 10 minutes, I can miss an occasional deadline. It is okay. Okay. It is still, I don't like it. I don't like missing the deadlines, but from time to time it is okay to miss a deadline. Usually these are called soft real-time systems. Okay, soft real-time systems, and usually entertainment systems like a embedded media player, right? Media player. Let's say you have a small screen device. It plays your videos or it plays your music. Okay, so this is supposed to show 24 frames per second, FPS. Okay, So if it shows 24 frames per second for the whole day, that's fine. But let's say in a given minute, sometimes I showed you 23 frames per second. I missed the deadline. In a given minute, maybe I can tolerate it because my eye is not that sensitive. Even if I notice there is a small freezing with the video from time to time, I can tolerate. So it's okay. Okay, with the soft real-time system. But for the hard real-time system, let's say your ABS brakes on your car, on your automobile, you cannot make those kind of assumptions. You cannot say that, okay, I will miss a deadline from time to time. It's okay. No, this is serious business. Okay, if you miss a deadline with the ABS brakes, you're gonna crash the car. Maybe you will lose lives. You will cause serious injuries to your passengers. That's not good. So for media players, maybe soft real time is okay, but for critical systems like nuclear power monitoring or the safety related car stuff, hard real time systems must be there. Okay, so I have questions. What is the logic behind less than? Okay, what is the logic behind less than 1? Kamil says. Well, I mean, if this is greater than 1.0 means that, okay, how can you make this greater than 1.0? You will say that I have two processes. Process 1 is going to take 100 milliseconds and it's going to run every 200 milliseconds. Okay. And process number 2, again, it will take 150 milliseconds and it will run at 200 milliseconds. So every 200 milliseconds P1 has to run. Every 200 milliseconds P2 has to run. So if you add them up, 1 over 2 plus 15 over 20, so it's going to be larger than 1.0. So you cannot schedule them on a real-time system. Why? Because let's say this is 200 milliseconds, 0 to 200. Inside this 200 milliseconds, P1 will run. P1 will take 100 milliseconds. And after that, I need to run P2. P2 will take 150. So I cannot fit these two into the single 200 millisecond window. 1.0 is there, okay? Mustafa, firm real-time systems, yeah, I mean, if you like to call it that way, yes, hard real-time systems. You may, I don't remember seeing that term firm RT, but I think it might refer to that hard real-time systems. Okay, so let's move on. I think there is a small example from the book. The book says that a soft real-time system with 3 periodic events with periods of 100. So P1, it will run in 100 milliseconds. Okay. What is going on with this pen? So P1 is going to take 100 milliseconds to run. P2 is 200. P3 is 500. No. P1, the period of every 100 milliseconds, P1 is going to run. Every 200 milliseconds, P2 is going to run. And every 500 milliseconds, P3 is going to run. Okay. When P1 runs, it will take 50 milliseconds. So P1 will take 50 milliseconds to run. P2 will take 30 milliseconds, but P2 is going to run at 200 milliseconds. And P3, it says that I will take 100 milliseconds and it is 500. So all you do is you just divide them and add them up. Okay, so this is 0.5 and this is 0.15 and this is 0.2 and the total is 6585. So 0.85 is less than 1.0. So this is schedulable. Okay, good. So schedulable real-time system is like this. Good. There are no questions. Maybe I can continue. Of course, these will say that I am going to run at every 500 milliseconds, but there could be some aperiodic events like this one. Sometimes they don't depend on the periods. Sometimes they don't have any periods. They from time to time they can run. From time to time they will not run. So if you have such a system, then engineering such system and making a decision that the system is runnable is going to be harder to calculate. Okay, so engineering such systems is harder. Again, we are not going to go in details of the real-time systems. There are this is a specialized topic, but it's a very popular topic too. And I think we are gonna offer a real-time operating system course next semester again. Orhan Hoca usually offers that course as an elective course. Okay, so these are the real-time systems. We talked about batch systems, interactive systems, and real-time systems. And let's go back a little bit. And we never talked about at the beginning. We said that threads are the same for us. I mean, scheduling between threads and scheduling between the processes are the same thing, kind of thing. But in reality, they are different, of course. Let's say we have a picture like this. Okay, we have a picture like this. I have two processes, 1 and 2. In process A, I have 3 threads. In process B, I have 4 threads. And these threads are managed using the user level thread libraries. Okay, so that means that the kernel doesn't know that there are 3 and 4 threads in each process. The kernel knows that there are 2 processes, and it switches between these 2 processes. That's what the user that's what the kernel knows. Okay, that's what the kernel knows. So the kernel will let process A to run, then it will switch to process B. But inside process A, I have 3 threads, so this is possible as a scheduling example. A1 runs, then A2, then A3, then A1, A2, and A3. So a round robin is running. Okay, so with my scheduling algorithm, round robin is running within this process A. But this would not be possible. A1, let's say this is 1, 2, 3, and 4. A1, then B1, then A2, then B2, and A3. This is not possible because I am not scheduling my threads with the kernel. Okay, when I say that as a kernel, when I say that process is going to run, I know that this will happen. When I say process B is going to run, then in that case I will say B1, B2, B3, B4, and B1 and B2 again. Okay, so with the kernel level threads, the upper part is possible, but lower part is not possible. Okay, if I do the same thing with the kernel, sorry, I think I phrased it wrong. With the user level threads, this is possible, and this one is not possible. These are the user level threads. With the kernel level threads, anything is possible. The kernel might say that, okay, A1 is going to run, then B1 is going to run. Let's say this is B. B1 is going to run. Then again, A2 is going to run, and then B2 is going to run. So this kind of switching is possible with the kernel level threads. So it is more flexible. Of course, okay, question. Which one is better? Doing this scheduling as a scheduling thing. A1, A2, A3, B1, B2, B3, A1, A2, A3. Is this one better, or how about this one? A1, B1, A2, B2, A3, B3. Which one is better? Of course, the upper one is possible with the user level threads, also kernel level threads too. The lower one is only possible with the kernel level threads. Okay, Mustafa says the first one is better, and Kamil says the first one is better, and just other people depends on priority. What do you mean, Yasin? What do you mean depends on priority? Their priorities are all the same. Their priorities are the same. Hussein says that first one is better because there is no context switch. Well, it is both true and false because, I mean, when you do this, there is a context switch here and there is a context switch. But this red context switch is more expensive than the green ones. Red context switches are more expensive. Why? Because you are changing your address space, right? You are changing your address space. With this one, with the second one, it is all red. Okay. Of course, there is a cost of switching from A1 to A2. Why? Because you still need to save your registers, your stack pointer, your program counter, etc. But it is not as expensive as switching from A3 to B1. Okay. Okay. So we like the first line better, but again, the first line could be achieved with both user level threads and the kernel level threads. Line 2 could be achieved only with the kernel level threads. So what was the biggest problem with the user level threads again? What was the biggest problem with the user level threads? Blocking system calls. Yeah, that's correct. Exactly. Blocking system calls is the biggest problem with the user level threads. If one of them blocks, the whole process is going to be blocked, even though, let's say, A1 blocked, even though I know that A2 and A3 can continue, the whole process is going to be blocked with the, not this case, but with this case, user level threads. We know, okay? And again, another problem, the similar problem is the, I cannot get benefit from the multiprocessors because with the multi-threading, I cannot run my threads on separate processes because I am at the user space, not at the kernel space. Okay, so good. But of course, the advantage of the user level threading is it is much faster. Why? Because I don't have to go to kernel and come back again. Everything is handled in the user space, so there is no context switching. Context switching in the classical case. So those are the nice things. Another nice thing about this Another nice thing about this user level threads is that they can employ application specific thread scheduler. An application specific thread scheduler. Question. I have a question now. In fact, I think I have an. Oh, okay. I spent some time last night and I prepared a small quiz for you. So it is quiz time. I will give you a quiz now. Quiz. Where are my quizzes? Quiz. Where is okay? Where is the? Okay, maybe we should do this. Assignments. Yeah. this one. Okay, I will give you a quiz. Okay, it is 11:15. Let me make this 11, not 15, but 17. Close date. Okay, good. So I made the assignment. You get the assignment. Okay, go fill that assignment now. Did you get the assignment? I don't see it here. Do I see it? Yeah, okay. So you have 1 minute. And while you are working on it, let me give you your... No, it says view assignment. I assigned it. I will give you another assignment. No, not assignment. I will give you not as discard. Okay, discard. Where are my assignments? Okay. I will give you another quiz. Yeah, that's the attendance quiz. Class attendance. Next. This form is not currently accepting responses. Well, I mean, you had only 1 minute. You missed your chance. So you got a 0. So let me make this assignment 11, and this is going to be AM 11:25, and close date is this too. Done. I don't care if your internet is slow. I don't care. No, it's just a simple testing. Okay, it's not going to be graded seriously. I will give you, but this one is serious. Let's do the assignment. Let's do the attendance. Okay, you have 5 minutes for now. Okay, so let's look at this scheduling thing. How many people did it? Viewed, some people viewed, some turned in. Nobody has turned it in. Not turned in. Some people have viewed it. Let's see if I have... No, nobody could have done it. Okay, nobody could did it. So that means that was a failure. Okay, let me give you the same assignment again. Same quiz again. Same quiz. Yeah, OS quiz. Next. Okay, I will give you... Why? This is so stupid. Okay, 11:22. And no lates. Well, anyway, I am not going to do it. No. It's just... I understand what's happening now. Yes, I just discarded it. And let me go back to general, my posts. No, okay, join. I am already in there, right? Okay, good. Okay, the question is this. I have a web server. Remember the web servers? We said that this is my web server. This is my web server. Okay. Inside my web server, I have a dispatcher thread. Okay. This dispatcher thread gets the jobs from the network, and it has a bunch of worker threads. Okay. So the question is this. Suppose that a worker thread has just blocked and the dispatcher thread and two worker threads are ready. Who should run next? Okay. Of course the answer is yes, it should be the dispatcher thread. Why? Because it doesn't make any sense to run the worker, because worker doesn't know what to do. It just hangs there, right? It waits for the dispatcher to assign some job. So why am I asking this? I am asking this because in this case only the scheduler inside the server knows who runs next. The kernel cannot know that. So with this kind of case, we like user level threads, because in the user level threads, let's say our dispatcher, okay, these are our workers. Only this library would know that this is a dispatcher, these are the workers. Okay. If I handle everything with the kernel level threads, then I cannot make this logical decision. So this is another advantage of user level threads. You may have your own specialized scheduler. Okay, you may have your own specialized scheduler. Otherwise, if you are using the kernel level threads, you cannot have this kind of flexibility. Okay, so good. Any questions? So I give you the attendance assignment. You have 2-3 minutes. I think 11:25 is the deadline. Okay, good. Any questions? Can't we give priority to threads in kernel level? Yeah, that could be Doğancan. That's a very good point. That could be another solution. You are saying that increase the priority of the threads, but usually remember threads are cooperative. They don't compete for the CPU usage. Okay, there is no preemption with the threads. Okay, priorities are for preemption. When something is preempted, which one is going to run next? Which one is the higher priority? Okay, so thread priorities are not implemented very often. Gökçe says that, can you explain why we need to use user level threads for this question? Because where is my picture? Where is my picture of the web server? Yeah, here it is. Let's say this is a single process. Okay, it's a single process. This is a web server process. This is a dispatcher. We looked at this before, okay, when we looked at the threads versus processes thing. Okay, this is a dispatcher and these are the worker threads. Okay, let's say this one has blocked. This one is blocked, is not continuing. So what should be my decision? Which one should run next? This one, this one, this one, this one, or this one? Okay, if the scheduler is a user level scheduler, that means that I can modify it. I know what's going on with the scheduler. I can modify it so that it runs this one next, because without this one starting, these four has nothing to do. They have nothing to do. Okay. So Pınar, I don't know what's going on. Does everybody, can everybody open the attendance? Can you open the attendance? Because attendance is gone. Okay. I said that it is, your time is up until 11:25. So I gave you 5 minutes for the attendance. People did it like 3 minutes ago. Okay, I will try to see what that problem is. Okay, so deadline is until tomorrow. that's 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 nice. I took a photo. Okay, Pınar, while you are at it, do you have a question? Pınar, do you have a question about the operating system? So you take your evidence with you when you take photos. Okay, Gökçe, you get the answer to your question. Okay, so let me see if I have another. Why can't I see all the questions? Okay, questions are here. So the Gökçe has the answers. Pınar is trying for 10 minutes, but I didn't make the assignment like 10 minutes ago. Pınar, you are trying to open something else. Okay, so I answered Gökçe's question. Yeah, okay, good. Pınar, let's talk about this later, okay? 60 people are like following this broadcast, okay? Okay, so that's the idea, Gökçe. Okay, so I think that's it about the scheduling. At the end of the chapter, there are two classical IPC related or process synchronization related examples, and I am going to talk about them. But before that, maybe I should take 10 minutes of break. Okay, so let's take 10 minutes of break. It is 11:28 now. Let's be here 38. So Pınar, other than you, everybody opened it, I guess. So I think you are clicking on yesterday's assignment. I don't know what's going on. I just made the assignment and it should. Okay, so 11:38 we will hear. Until then, I am turning off my mic. Okay, everybody, let's continue. Vefik Fradakman, homework is difficult? No, it is not difficult, Vefik. No, it's not difficult. And even if it's difficult, it is difficult to everybody. So I think you have how many days? How many days do you have more? So you have 8 days. In 8 days, you would write a new operating system. And we have given you more than 8 days, right? Okay, there is no change with the deadline of the homework. And we did not get a single question about the homework yet. Right? Are you there, Ilhan? Ilhan, are you there? Did you get any questions about homework? I did not get any. Anyway, okay, so let me go back to the course. And this is the problem. The problem is I cannot get rid of this stupid assignment thing. I cannot see your questions if I do that. Okay, maybe this is better that way. Just a minute. Okay, so it is better now. Okay, so that's the. Can somebody talk? I cannot hear anything. Is somebody talking? Well, in that case, that means that I am not. Okay. Somebody talk again. Somebody say something. Oh, okay. Now it's fine now. Okay. Okay. So this is our classical problem, dining philosopher's problem. The thing is this. I mean, this has nothing to do with philosophy or dining or food or forks, etc. I have a process number 1. I have a process number 1, and another process number 2, 3, 4, 5. There are 5 processes running, okay, and each process needs 2 resources to run, okay. This process needs these 2 resources. This one needs these 2 resources. These could be, for example, printers, plotters, scanners, or maybe a mutex, okay. For this process to run, it needs to get a mutex, this one, and mutex that one, okay. Get this mutex and get this mutex, and it will run. This one, it will get this mutex and this mutex, and then it will run. So they kind of simplified it. Vivek, you have a question? You have a question about the homework? Just send an email and ask. What is wrong with email? Do you have a question? If you have a question, you can ask it right now. Then after the class, when I stop it, okay, you may ask your question to me or to Ilhan, okay? So I have process number 1, process number 2, process number 3, 4, and 5. Okay, and these are the resources. This one needs, let's say, let's call them mutexes. Actually, this is mutex 1 and mutex 2 and mutex 3. So for P2 to run, it should have both of these mutexes, and for P1 to run, it should have both of these mutexes. Okay, that's what the idea is. But they kind of idealize this scenario, and they say that there are 4 philosophers sitting around the table, 5 philosophers sitting around the table. Okay, they are eating pasta. Okay, they are eating pasta, so they need 2 forks. For this guy to eat the pasta, he needs these 2 forks. But if he eats, this one cannot eat because he needs these 2 forks too. Okay, so how would you solve this problem? How would you solve this problem? That's the question. So if I say that only one process can run, let's say only P2 can run and all of them should wait, that should work, but that's kind of inefficient, because why? When P2 runs, either P4 or P5 can run too. Why am I stopping them while they can run, right? So how many out of 5 can run at the same time? Question. How many out of 5 can run at the same time? At most 2, right? 3 cannot run. 3 cannot run because for this to run, it needs 2 forks. There are a total of 5 forks. Okay, 5 forks is not enough to run 3 processes, or 5 mutexes is not enough to run 3 processes. So at most 2. So let's find a solution that makes it possible to have 2 philosophers eat at the same time. Okay, so let's look at the solution. This is the first solution from the book. Okay, it says that okay, n is 5. Do you understand this one? I is from 1 to 5. The philosopher number I says that I am thinking now. I am not hungry, but when I am hungry, when I like to eat, I will take fork number I, and I will take fork number I plus 1 modulo n, so that it goes like 1, 2, 3, 4, 5, and 1 again. Okay, so these are the forks, and these are the philosophers. So the philosopher number 1 uses fork number 1 and 2. Philosopher number 2 uses fork numbers 2 and 3. 3, 4, 5. So the philosopher Beyza says that the video is not in sync with your voice. I don't know what to do, Beyza. I have no control over that. Maybe if I stop this and run it again, would it help? So lots of people are complaining from the same thing. Did we have this problem yesterday? Mustafa, we cannot go back to YouTube. The dean says that there is no YouTube. Don't use YouTube. Is anybody having no problems? Is there anybody getting this right? Is anybody getting this right without any sync problem? And you had this problem. I don't know what to do. I mean, that's what they say. They told me. They told me don't use YouTube. Okay, People at the engineering faculty, they don't understand anything. They never teach any classes, but they force us to use this kind of stupid stuff. I don't like to use this, that they make us do. Okay? No, Kamil, no, I cannot use anything else. It has to be either Zoom or this one, or no Zoom. Either a Moodle or Teams or something else. I don't know. They are all stupid stuff. Okay, I mean we did with the YouTube. YouTube was even worse than this. I know that. YouTube was worse than this. I mean with the YouTube, there was maybe 30 seconds of delay between what you write and what you do. Okay. Talai, did you watch any YouTube videos in live stream? The sync problem there is even worse. There is 30 seconds of delay. Okay, when you ask a question, I get your question 30 seconds later, and when I give you answer, it gives you again 30 seconds. So there is a 1 minute turnaround time. Okay, so nobody's getting this right. So everybody's getting with the sync problem. Is anybody getting this right? Voice on the screen, I don't know what that means. I don't know. I mean, I cannot. Some people get it right, some people don't. I mean, there is not much I can do, and I will try to not write much, not talk much. Okay, this is what I'm gonna do. This is what I'm gonna do. I will upload the. I am recording all the YouTube video, all the videos with the OBS, and I will upload them to YouTube. And if you miss something, I will let you watch from the YouTube then. Okay, Beyza, nobody could take the quiz in time. Nobody was able to answer. The time I gave you was too short. Okay, let's back to the course. Okay, these are the fork numbers and these are the philosopher numbers. As I said, philosopher number 5 is going to use fork number 5 and fork number 1. And after he takes the forks, eats and puts them back so that they are available. So what is the problem with this case? What is the problem with this picture? This is from the book, but it says it's a non-solution to the dining philosopher's problem. The problem is this. Barish, can you be more specific? What do you mean by deadlock? Taking and putting forks should be in critical region. Why? It's a shared resource. Let's talk about. I mean, what do you mean? What would happen? Let's say this is in critical region. This is in critical region. The problem here is this. If let's say if 5 processes are running at the same time, process 1 started thinking and it decided that it will take the fork number 1. Okay, so the process number 1 took fork number 1, Okay, the process number 1 took the fork number 1, and there is a switch happened. Process number 2 took fork number 2, and switch happened again. Process number 3 took fork number 3. So this is what happened. Let's say this is what happened. Process number 1 took fork number 1, and 2 took fork number 2, right? And 3 took fork number 3 again, and 4 took fork number 4, and 5 took fork number 5. Okay, so these are the switches that are happening. And then switch happened. Process number 1 is trying to take the fork number 2, but it cannot. It waits. Process 2 is trying to take the fork number 3, but it cannot, it waits. So all of them are blocked. Nobody can continue. Everybody's waiting for something else, okay? Everybody's waiting for something else. That's the problem. So I think this is what Baruch Shahin means when he says deadlock, okay? So how are we gonna solve this problem? Let's solve this problem. Let's solve this problem like what people are saying. Let's say this should be in critical region. Okay, let's do this. Let's do this. Let's do this. This is here at this position. Down mutex, right? Up mutex. Does this solve the problem? Does this solve the problem? Doğancan says no. Why? Because I mean, if I am the process number 1, if the mutex is available, I take fork number 1, I take fork number 2, and I should not worry about anything because nobody else can take fork number 2 because I get the mutex. I mean, if I get the fork number 1, after that there's a switch happened, second process cannot go into this region, right? So Doğancan, why not? Doğancan, just talk, okay? Open your microphone, use your microphone. Are you talking? There is something funny happening. Why I cannot hear anything? Doğancan, are you talking? Can somebody talk? I cannot hear anything from anybody.
Hello?
Yeah, okay. No. So tell me what is wrong with this. Doğancan, can you tell me what is wrong with this? Doğancan is out.
If we do it this way, we block every other philosopher at the same time. And only one philosopher can eat.
So that's kind of solves the problem, but what did we say at the beginning? 2 out of 5 can eat at the same time. This will block everybody else. So this is kind of safe, but this is not multi-programming. This is blocking everybody else. That's one solution for the raised conditions actually. If you block everybody else, finish your job first. Nobody's going to be hurt. But that means that you're not doing any multiprocessing. You're blocking everybody else. So that's not a good thing. How about this? How about this? Up mutex. Okay, eat and down mutex and up mutex. How about this? Did this solve the problem? Because when I am eating, right? When I am eating, I am not holding any mutexes. Everybody, other people can come in. Okay. So did this solve the problem? The answer is no. I mean, what was the idea? Somebody said that we should. I mean, those forks are shared resources. Okay, those who said that. Taking and putting forks should be in critical region. Ahmet Yasir said at the beginning. Okay, so I did that. Downing the mutex and upping the mutex, it is done this way. But this is not a solution either. This is not a solution either. So what is the problem? The solution is a little bit more complicated than this. So the thing is this, okay? No, because when two people have forks, if somebody tries to take, you're not allowed to put back. If somebody, that's kind of, it is kind of, yes, that's what it is actually. If somebody is, let's say, as process number 1, I took fork number 1 and I took fork number 2, right? As a process number 1, I did this. I took fork number 1 and fork number 2, okay? And I started eating, okay? I started eating. While I am eating, process number 5 came in. Process number 5 came in, and it said that I will take fork number 5, but when it comes to fork number 1, it cannot take it, so it will get blocked here. So I am holding the lock, and I cannot hold fork number 1, and I am waiting there. And now when the process number 1 is done with eating, he cannot put the fork back because somebody is holding the mutex. Understand? So this doesn't work. I mean, there is no communication between this part and this part. I can take these forks while I am eating. If somebody is trying to get one of my forks, okay, they will be blocked in there, and that's not going to be good, and I am not allowed to put it back. Okay, so I should kind of check if the forks are available. If they are available, then maybe I should go in there. But to check the forks are available, I need another mutex. Okay, is this clear to everybody? So I have a solution from the book, and we will look at that solution right now. Is this clear to everybody? Okay, so this is not a solution. This is not a solution. How about try lock? It's kind of like that. Okay, if both of them are available, then I will lock them. Okay, lock them. But again, there could be problems with the unlocking. Okay, there could be problems with the unlocking. So that's the idea. Let's see before entering the critical region. Let's see if both forks are available. Okay. But when I am done, if somebody is waiting for these forks, then wake them up kind of solution. So let's look at the solution from the book. Okay, it is not that complicated. This is what remember, this is what philosopher did. Process number I, or the philosopher number I. This is what it did. Are we having the same synchronization problem? Maybe I should talk a little bit slower. Is the synchronization problem a little bit better?
It's still the same.
What kind of delay is that? How many seconds?
Your writing comes a bit late, like 2-3 seconds.
Okay. Maybe if I talk a little bit slower, that will be kind of solution. Approximately 2 seconds. Maybe is there some, in YouTube you had that delay button somewhere. Okay. So if I do this, I can stream it using YouTube right now, start streaming. And if I'm worried my bandwidth will not be enough for that one. No, if I do that streaming, I need to, no, I will have to do this later. Okay, I will try both streaming and doing this. But I don't think that my bandwidth will be enough. And that's going to give me some other problems. Anyway, let's come back to this one. So I will be a little bit slow to write stuff. So this did not work, and the previous solution we did not like. This philosopher number I is running this loop. Now the philosopher number I is running this loop. It says that think, okay, so produce some data, take forks, both forks, eat, and put forks back. Okay, so inside this region I am using both resources. Inside this region I am not using any resources. So these are some defines. I have 5 philosophers. This is my left, this is my right. You understand these, right? So if I is, let's say, if I is 2, if I is 2, my left is I plus 5 minus 1. That means 2 plus 7 minus 1, 6 modulo n. Then this is 1. Right is 2 plus 1 modulo 5 is 3. So for I is 2, left is 1, right is 3. For I is 5. Okay, for I is 2. For I is 5. Left is 4 and right is 1, right? Okay. And I have 3 states. And I have 3 states. Thinking, hungry, and eating. Okay. And I have a mutex semaphore to control the critical region. And I have 5 semaphores. 1 semaphore per philosopher. And we are going to see how we are going to use it. And I have this state array and the semaphore array. In the state array, I am going to keep the state of each philosopher, either thinking, hungry, or eating. Okay. And the semaphore means it's a semaphore. It's not a counting semaphore, it's actually mutex. Okay. So let's go check this. Maybe I should go to the book, and book is where is my book? My book is this one, right? Or this one. Okay. So let's go to the book, because in the book I have the continuous okay, there it is. Do you see the book, right? You see the book, right? What happened? Contents and the dining philosopher problem. Yeah, okay, here it is. There's not a solution. Here is the solution. Okay, so philosopher number I, it says that take forks and put forks. Take forks this way. Okay, it says that first down the mutex and up the mutex. You know what? I need to open this from the other program 201. Okay, so that I can write on it. Okay, so this one says that take forks. So this is my critical region. This is my critical region. Inside the critical region, remember my state array. Okay, these are the data structures. I is the philosopher number. M is the mutex. S is the semaphore array. State is the state array. So let's say I is 0 and I called take forks. Okay, so down mutex, now mutex is 0, nobody can enter it. Okay, and state I is hungry, so I will make, let me erase these and put my, okay, so at the beginning everybody is thinking. Okay, so my state I is hungry, so I will say that my state is hungry, H. So I like to eat, right? So I will call this function name test I, and then after that I will up my mutex. Okay, this is my critical region. I will up my mutex so that all other people can in, and I will down my SI. SI is this. So at the beginning everybody is already 0. Okay, so one semaphore per philosopher, at the beginning everybody is 0. Okay, so the important thing here is the test function. Let's look at the test function. I am trying to keep them, this one and this one, in the same shot. So what does the test do? Test does this. Okay, for let's say I is 0, it says that if state I is hungry, if I call this one, okay, I know that state I is hungry. If the left is not eating, if the right is not eating, then I will change my state from hungry to eating. Okay, I will change my state from hungry to eating. So my state will be eating. Okay, I change this one, eating, and then I will up my semaphore. So my semaphore will be 1. Okay, after I call this function, if I am hungry and if my left is not eating and if my right is not eating, then I am eating and I up my semaphore. And when I come here, I will not be blocked. Why? Because I up my semaphore, I will decrement it, and I will take the forks. Okay, so that's what it does. The test function does. So what did we say at the beginning? We said that what was the solution? We said that if I am able to get both forks, okay, that means that if my left and right is not eating, then I can eat. I am checking it inside my critical region, and after that I say that I will up my semaphore so that it can be downed. So that's how I enter my eating region here. That's how I eat. So let's say that my left or right is eating. My left or right is eating. In that case, I won't say my state I is eating, and I will not up my semaphore. When I come to this part, down SI, I will get blocked here because I did not up my semaphore. My semaphore is going to be 0 again, and I won't be able to continue. I will be blocked. So if one of my neighbors, left or right, or or both of them are eating, then that will get me blocked here. Remember, with the mutexes or semaphores, only down blocks. Up does not block at all. Okay, up just signals somebody else who is waiting for that one. So with the take forks function, I can be blocked either here or here. The reason for the block at this point is if the mutex is not available, I will be blocked. For this, the reason if I am blocked here is either my left or right is eating, or both of them are eating. So there are two reasons. Okay, so this is how take forks work. Take forks, then eat after I am done with the eating. Okay, and I will say I will put the forks. How does the put forks work? Okay, down mutex. So I might be blocked here if the mutex is not available. If the mutex is available, so I will say that I am not eating anymore. I am thinking, and I am calling this test function with my left and right. Okay, if I is 0, so I will call my left with what left is. If I is 0, what is left? Left is +1 +5. Okay, -1. Left is 5, right? Right is 1. No, 5, and no, this is 4. I start from 0, 0, 1, 2, 3, 4. Okay, I not from 1. Philosopher number 0, 1, 2, 3, and 4. Okay, there is no 5. So I will call this left with test with 4 and 1. Okay, so this is kind of interesting. I mean, when I take the forks, I code it with myself, and I'm calling with the neighbors. So it says that if my left neighbor is hungry, oh, that's interesting. If my left neighbor is hungry, if my neighbor's left, not my left, is not eating, if my neighbor's right, which is me, okay, is not eating, I am not eating, then I will say that my left is eating, and I will up my left's SI. So in a way that I am making the fork available to my left in case left needs it. What is the condition for my left to eat it? It has to be hungry. My left neighbor has to be hungry, and his left and his right are not eating. So I am upping their semaphores. If somebody is waiting there, okay, so I up them so they can continue. And I will do it with the right. If my right is hungry, if my right's left, which is me, is not eating, I am not eating. If my right's right is not eating, then make my right eating and up its semaphore. Okay. So the only case where put forks might block is this line, and then the critical region. Take forks can block in 2 cases, here and there. Okay. So that's the whole program. In a single page, and that's the solution. I mean, this can be generalized to any number of philosophers. 5, 6, 7, 10, 100,000, doesn't matter, and it should work. Okay, any questions so far? Why? Okay, Kamil has a question. Why do we need mutexes in take forks and put forks? Okay, why do we need critical regions in there? That's because I am modifying the state I. See, more than one function might be changing the state I. One of them is making hungry, the other one is making eating, okay? The other one is making thinking, okay? If three different processes call these functions for the same state I, they will be in a race condition, okay? Semaphores are not enough. No, they are not. I mean, this semaphore is for mutex, for controlling the critical region entry and out. The others are for left and right stuff. If the left and right is available. What was your idea? I think you said that. Let's check if both of them are available. If both of them are available, both of the forks are available, okay, if both my regions are neighbors are not eating, then I can start eating. That's the right part. But the thing is that how am I gonna put the forks back if somebody is waiting, right? So that's the solution. So that's a very smart solution. Somebody came up with this one. Okay, Ahmed has a question. Is this problem a common operating system design problem? Where do we come across a problem? As I said before, this is not a. I mean, okay, this is a operating system problem if you have more than one processes, but this is a multi-programming problem. This could happen, right? As I said before, I need the mutex for this one. I need the mutex for this one. And if both of them are available, I can continue. Otherwise, I cannot. Let's say in a database, okay, in a database, let's say this is a database of persons, let's say person names. And this is a database of person tax information. And this is a database of person health information. Okay, person health information. I might need the logs for that same person for both names and the tax information so that I can modify their tax information and the name information at the same time. But somebody else might need these two databases for changing person health information and the tax information. Okay, so this is a typical problem with the databases. And if you have more than one process working on the same database, then I need to be careful about these kind of problems. Otherwise, I will be in deadlock situations. Okay, Ahmed. So this is not a very rare, very off the wall problem. This is a common problem. We need to be careful about this. Dining philosopher's problem is a classical computer science problem. Okay. So I think I'm out of my time. Let's take 10 minutes of break. As we said yesterday, I will do one more hour of lecture, and I will start chapter number 3, memory. Okay. So it is 12:23 right now. Let's be here. Let's 30. No, it is 4 now. 12:34. Okay. So I couldn't write for. Okay. Good. See you in 10 minutes. Okay. So, oh, I forgot my stuff. So let's continue. This is it was a very nice question actually. I mean, sometimes the examples that we give you with this class might be a little bit not very practical examples, but these are actually practical examples. There is one more example from the book Readers and Writers Problem. This one, I think I will not. That's an important problem too, but I mean, if you are interested, just look it up. It's a nice problem too. The problem is this: you have a single database. If you are reading the database, there could be as many processes as you like. Okay, there could be 100 reading at the same time because reading doesn't break anything. But if somebody is writing to it, nobody should read it, right? So that's the problem. So you should set up your mutexes semaphores in a way that as many readers as possible are allowed at the same time. But if there is one single writer, nobody else is allowed. Okay, so you should do your locking mechanism this way. Okay, so I think I will be with this one. I will be. Let me close this one. Save it maybe for later use, and let's go back to our, where is my, okay, processes and threads chapter, and I think we will be done with this chapter now. Do we have any problems with the questions about the processes and threads? That was a very long chapter, but that was very important chapter again. Let me go to my slides and let me open up my new chapter slides, which is about memory. Okay, any questions? Let me see how many people I got. I have how many people are there? If I do this, $75 people. Okay, good. Okay, so chapter number 3 is memory management, which is as important as the process management and processes chapter. Let's see. In 1960s, remember this machine, IBM 7094? It has 32 kilowords, and that was $15 million computer. Nowadays, our average home computer is maybe 150,000 times more memory. So lots of more memory. That it may look like we have solved the memory problem, because in 1960s, if we had this kind of memory for the top computer of the world, and in 1960s they solved lots of problems with the computers. So if that computer was enough for the most demanding job in those days, then I should be fine for a home computer right now, but that's not the case. No. People say that programs expand to fill the memory available to hold them. So we need to be careful about our memory. We need to manage it right. We need to be careful about our CPU too. I mean, doesn't matter how large memory I have, doesn't matter how powerful CPUs I have, doesn't matter how large my secondary storage is, it will be filled up. The software demands expand much faster than the provided hardware opportunities. Okay, so that's the rule for the memory too. So we need to spend lots of time to manage our memory. Okay, main memory is again like a CPU. It is a resource. Okay, CPU is time multiplexed, main memory is space multiplexed. Okay, so if this is my CPU, if this is my CPU in my timeline, I would say that from this time to this time it is P0, from this time to this time it is P1, from this time to this time it is P2. But with my memory, it's like this, one long linear space. This is P0, this is P1, maybe this one is P0 too. Sometimes I do that. Okay, so in space wise I do the multiplexing. So I need to manage this using appropriate routines. Okay, and it is operating system who does this management, because I cannot let processes manage their memories themselves. That would be too difficult for them. Also, that would make it too problematic in terms of protection. Okay, protection. Well, at the beginning it was very simple actually. At the beginning, managing your processes and managing your memory it was very simple for the first generation and the early part of the second generation computers. Why? Because I had a single user. Okay, with the single user there was not much operating system. I didn't get any help. There was no input output. I was programming everything by the punch cards and everything, that kind of stuff. So it was so simple. For the memory management, there is no memory management because all the memory belonged to me. But things has changed because I have many programs running at the same time in my memory. So I have to share my CPU with other processes, and I have to likewise I have to share my memory with other processes. Okay, so these are some examples. Okay, A is from the 60s. This one. This is my memory, early version of operating systems. I put them at the beginning of the memory, address number 0 to some number. On top of it, I put my user programs. If I didn't have any, if I had no protection, memory protection, then the user program can run and can wipe out the whole operating system. Okay, so this was the case in 1960s because I didn't have the powerful enough hardware to provide protection. Okay, in the 80s, of course the mainframes or the top powerful computers didn't have this problem, but the early personal computers had the same thing. Okay, they say that I will put my operating system again at the beginning of the memory. My user programs are there, but some part of the operating system, for example, the device drivers, they will be in read-only memory, so they cannot be wiped out, and they will stay at the top of the memory. So that was the case for the 1980s. Again, they are facing the same problem that they had faced in 1960s. And sometimes my operating system is like this for embedded systems. User programs are there and my operating system is at the top in a ROM, read-only memory. So there is no wiping out problem. So if I don't have any memory abstraction, if I don't do any memory management with the operating system, these would have been solutions, but this is not the case anymore because I like to use many programs and I like to share my memory amongst many programs. That's what I like to do with the no memory abstraction. No memory abstraction is like no CPU abstraction, no processes. No processes means that there is only a single thread. It takes a CPU and it runs. That's it. No memory abstraction means that my thread, my execution, my program sees the physical memory and it performs everything on the physical memory, and that's what it does. Okay, that's what it does. And what I'm saying is that for current computers, these are not possible anymore. I have to be more careful, like I did with the CPU management, like the processes, the idea of processes. I need to come up with ideas to abstract the memory so that I can manage it. I can make it fairly usable amongst the processes. Okay, so the early versions of loading more than one program inside my memory and switching between them. Okay, running multiple programs without memory abstraction. I'm not going to provide an abstraction. Operating system doesn't provide any memory abstractions. Let's say I have two programs. As soon as the program starts, program A, it says that jump to address number 24. It moves some stuff, it adds some stuff, and it goes on like that. It looks like my memory is maybe 16K for this process. Another process is this, another program is this. It just, whenever it starts the program, it says jump to address number 28 and compare something and do something and do something, and etc. Again, this one is 16K too. Okay. If I run only this program or only this program on my computer, there is no problem. But if I like to do round-robin scheduling between these two, okay, switch between them, I need to keep both of them in my memory at the same time. And I need to provide space for them. Okay, this is what I do. Okay, let's say now I have physical memory, 32 kilobytes of memory. And I did this. At the beginning of the memory, I placed my first program. And now I have my second program. And I am kind of trying to switch between this one and this one. Okay. Do you see any problem with this approach? Do you see any problem with this approach? Am I talking to myself? Oh, okay. Ahmet Yasir is always there. Ahmet Yasir, you are not a robot or something like that, right? You are a real person. You are always there because the processes can access other processes' memory. That means, okay, not a robot. Okay, when a robot says I am not a robot, don't believe that robot. Okay. You know the Turing test, right? Turing test. Okay. Anyway, never mind. Okay, so that's a good thing. Ahmed says that processes can access other processes' memory. So there's a protection problem. Yes, that's true. That's true. I mean, within this program, within this process, I can change stuff in these addresses. There is nothing that prevents me. Okay. There is nothing that prevents me from doing so. Okay, that's a maybe secondary problem. But the more important problem is something else. That's a very, I mean, let's say these are threads, they are cooperating and they are not trying to reach, or maybe they are supposed to reach each other's address space. Maybe, I'm not just making up. But there is a more important problem than that. So what is more important? What is more important? There is a very serious problem there. I mean, if you look at this picture, look at the instructions. Yeah, Furkan, that's exactly. Jump 28. This one here tries to jump to this location. This one tries to jump to this location. Okay. This one is trying to jump to this location, but this one is trying to jump to this location instead of doing this, right? Because they jump 28. I mean, it is not as simple as putting the program at the top of the other program. That's not going to be a good solution. So what you need to do is maybe find these kind of absolute addresses whenever they are. And when you are loading this program, add this number to those absolute addresses. Okay, add this number to those absolute addresses. That's called static relocation. Okay, static relocation. At program load time, the execution address is known. Okay, add the actual offset of the presumed location specified by the compiler and linker. So I know this address, the location of the program, and my compiler and linkers are telling me that, okay, these are the memory positions where you need the absolute memory positions. So at the end, you will add all of these. So the cost of is this. You need the number of words and the number of to be located. You need to know them. And when you load your program, you have to modify them. So loading is a little bit more difficult, and your compilers and linkers has to provide all this mechanism. And of course, there is no protection, as Ahmed said. Okay, so this static relocation kind of works, but it is not exactly what I want. And it did not provide any abstraction, actually. I mean, it's the same memory. It's the same memory. And when I write my programs, I need to be careful because I am telling the operating system that these locations has to be modified when you load this program to your memory. Okay, again, I don't have any memory abstraction, and it has some serious problems. And then the other thing is that, remember, I said that in my program I have 16 kilobytes of physical memory. So either this one or this one can work. I don't have enough space to fit both of them at the same time in my memory. Okay, I don't have space to fit both of them. Well, you might say that in that case, unfortunately, you won't be able to run both of them at the same time. No, there are some good solutions. Maybe load half of it with this program, and run them at the same time. If I need more data, load them from the disk. Okay, there could be those kind of solutions. Okay, so static relocation, lots of modification of the code and no protection, and the programs may not fit into my memory. On this machine that I'm using right now, I think I have 8 gigabytes of memory. But if I look at all the processes, these are my processes. Okay, if I look at all the processes, I don't know how many I have. Let's say 1, 2, 3, 4, 5, 6, 7, 8, 9, 10. 10 is here. 10 is here. And how many pages do I have? I have 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12. I think 24. So I have 240 processes running. Okay. So if each one is taking like half a gigabyte of space, there is no way that that's going to be enough. Okay, there is no way that that's going to be enough. Oh, by the way, lots of good stuff happening here, right? Okay, power usage. Somebody's using my power a lot, very high OBS because I am recording it, and Teams is using very high power, and trend is high. It's getting higher and higher. Do I have my priorities? No, I think I need to look at my other view of doing stuff. Anyway, so I mean, 8 gigabytes is a lot of memory, but it is not enough to fit 240 processes at the same time. I need to do something about this.
So someone muted you.
What's that again? Ahmed, you ask a question? Oh, somebody muted me. Somebody. Okay, somebody muted me, and I got. Okay. So I was talking about my process manager, my task manager. I said that I have 240 processes running on my computer, which has 8 gigabytes of memory. 8 gigabytes is a lot. It's much larger than that $10 million computer of 1960s, but it is still not enough to fit all of them at the same time. So maybe I should not try to fit all the programs in my memory at the same time. That's what I want. That's what I said. Okay. So that muting guy is just muted me. I think they are doing it accidentally, because once you do it by accident, you cannot unmute it. Okay, good. Let me keep it here so that I can maybe see it. So the idea is let's introduce another abstraction. Like the CPU abstraction, we like to do the memory abstraction. Okay. This abstraction name is address spaces. Okay, double frame address spaces. Okay. Address spaces, the definition is this: is the set of addresses that the process can use to address the memory. So a process thinks that it has certain number of addresses that it can address, and it doesn't care where those addresses are in the physical memory. So the process runs as usual. It thinks that it is the only program in memory, and it will start running and it will do whatever it wants to do, and it will terminate. Okay, so it thinks that it has a process like a CPU. It has a CPU because I abstracted the CPU away with the concept of process. Now I am introducing this address space, and the process thinks that it can do whatever it can do. It can do whatever it can with the address spaces, the set of addresses. Okay, each process should have its own address space, independent of those belonging to other processes. Okay, if this is my memory, okay, the OS has an address space, process 1 has an address space, process 2 has an address space, but the process 1 thinks that, okay, all the addressable places in the memory belongs to process 1, and P2 thinks that all the addressable places belongs to process number 2. Okay, that's what they think, because operating system abstracts the details away. Operating system makes them believe that they have the whole memory to themselves. That's the concept of address space. So, I mean, address spaces and processes are very similar in that just as the process concept creates a kind of abstract CPU, okay, address space creates a kind of abstract memory for programs to live in. Of course, we need to address the protection and relocation problem. I mean, without solving the protection and relocation problem, I mean, P1, when it runs here, it should run the same. When it runs there, it should run the same. No problem. It should be exactly the same solutions. So relocation should not be a problem. Also, P1 and P2 should not be able to access each other's address space. So protection and relocation should not be a problem. And again, there should not be any problem of I don't have enough space for this program to run on this machine thing. Okay, I should be careful about that too. Okay, so the whole, by the way, this is misspelled address space. Okay, this whole chapter number 3 is about address spaces. How am I gonna provide this protection, relocation, and not much memory problem to the processes so that they think that they have their own address space? So we are going to abstract away the complexities of memory. That's what we are going to do with this chapter. Okay, any questions so far? Okay, so let's look at some of the early examples of kind of address spaces. Okay, base and limit registers. That's the solution. The solution is this. Okay, the solution is this. Let me show you from this example. Remember those two programs? Let's say I have enough memory, 32 Ks, Okay, instead of doing static relocation, this is what I do. I have two special registers, base register and the limit register. These registers are inside the CPU, so CPU has to support the base registers and the limit registers, these two. Okay, so whenever I switch from one process to another process, I need to see that they are like program counter, they are like stack pointers, they are like regular registers. Okay, the function of base register is this: if CPU executes an instruction like this, jump 28, this number is automatically on the fly added to this base register number. See, this base register number is the same as this number. That's the starting address of the program. For this program, the base register would be 0. Okay. Limit register is the top address of the program. So inside this program, if I like to access a memory location, okay, the final address should be between this number and this number. So it should be between base register and base register plus limit register. So each program can run this way. They think that they have 16 kilobytes of memory address. That's fine. And they can live a very happy life, right? No problems in this case. So I don't have this problem of static relocation. I am not changing anything inside this program while I am loading it, right? All I need to do is my CPU has to provide these two registers, and on the fly, when I make a memory reference, either reading from the memory, writing memory, referring to memory, jumping to some memory location, doesn't matter. I need to add all of those numbers with this base register. When I do a context switch, okay, if I context switch from this process to this process, my base register becomes 0, right? And I need to save this base register in my process table. Okay. So do you see what kind of problems do you see with this solution? It's a simple enough solution. Of course, you need to get help from the CPU. CPU has to provide this base and limit registers. Do you see any problems? It kind of solved this. By the way, it solved the protection problem. How it solved the protection problem? Because any memory position that you're going to access has to be between base register and the limit register. If you are reaching outside of this region, base and limit register region, then somebody if I was saying that if somebody is trying to access outside of the region that I'm allowed to, then it will be beyond this limit register. So the CPU would know. So I would get help from the CPU to provide. I would get help from the CPU to provide protection. Okay, to provide protection. Okay, so I saw that problem. Protection is gone. Address spaces, the programs think that they have their own address spaces. Okay, too. What other problems do I have? What other problems do I have? Protection, relocation, what else? Too much address calculations. Yeah, that's one problem. I mean, whenever you make a memory reference, you will have to do this addition. Addition is very expensive, actually. Why? I mean, in terms of hardware implementation, addition is expensive. Why is addition expensive? It is more expensive than comparison. Addition is expensive. Why? Because with the addition, you have to do this. How do you add two binary numbers? You add them, right? Add them and you carry them, okay? You have to start from the least significant bit and you have to go from right to left. So it's a sequential thing, okay? So addition is expensive. We don't like addition, but let's say our CPUs are fast enough, and with the implementation they are very fast adders. Let's ignore that problem. The other problem is if I don't have 32 kilobytes of memory space, then there is no way I can fit them in my memory. So I still did not solve that problem. I still did not solve that problem. And the solution to that problem will come later. So let's ignore that problem for now too, but the problem is there. So dynamic relocation based on limit registers. Okay. The contents of the base register is added to the all memory references, and any memory reference larger than the limit register is invalid and cause a trap. Trap means that CPU says that this instruction execute an illegal operation, and I will interrupt it, and I will ask the operating system handle it. So CPU provides this mechanism for me. Okay. So large programs do not fit into the memory. Maybe the solution could be swapping and virtual memory. Swapping, we are going to look at it in a few minutes. Virtual memory will come maybe next week. Okay, so let's look at the swapping. Swapping is this. If my physical memory is not large enough to fit all the programs, then maybe I should swap. Write the entire program out to the disk when it is blocked. Okay. When it is ready to run again, read it back to the memory. Okay. So that means that I am writing back and forth. I am transferring data back and forth between my memory and the disk. Disk is something slow. Remember the latency table that I showed you last time? It is millions of times slower than the main memory. Yeah, but this is, being slow is better than not being able to multi-program. So we are going to take that hit and we are going to use the swapping idea. Swap programs back and forth between the memory and the secondary storage. Here's an example. Let's say I have this is my configuration, initial configuration. I have my operating system at the bottom. Okay. I am using base and limit registers, so there is protection available. I loaded my program A, then I need to load my program B, and I need to load my program C. So I have enough space for all three of them. I am running. Then I need to load program D, but there is not enough space for program D. So what am I going to do? I need to either swap A or B or C. So the operating system makes a decision, says that I am going to write A to the disk, so this space will be available. So I loaded program D to this position. And then if I need program A again, see, even though I have enough space for program A, because if I add this part with this part, okay, space is enough, this part and this part, the space is enough, but I cannot load it because I need this contiguous space. So unfortunately, I am swapping out B to the disk again. Space is enough. I am loading A again. Okay. So this problem here, even though I have enough space for a new program, I cannot load it, is called fragmentation problem. That's a problem we are going to see many times. And to prevent the fragmentation problem, I can run this compacting operation. How do you do the compacting operation? Move B there and move C down there so that I can have enough space at the top of the memory for the program A. But moving the whole program from one space to another space is too much work. That's going to be expensive. Maybe it is less expensive than writing B back to the disk. By the way, when I write the program B to the disk, I don't write the whole program, okay? I don't write the whole process. I only write the data section. I don't need to write the program section, right? The instruction section, because instructions are not changing. Only the data changes, so I write the data section only to the disk. So I don't write the whole process to the disk. But when I load it, of course, I need to load the whole thing, including the instructions and the data. Okay, fragmentation and compacting is two things that I need to be careful about. I have enough space, but due to fragmentation, I couldn't fit program A, so I need to swap out program B. Okay, so Ahmet has a question. Do we read instructions from hard drive? Yes, of course. I mean, since we didn't have enough space for those programs, I had to swap it out. Yeah, I read those instructions from the hard drive and load them to the memory because I forgot about them. I mean, writing is efficient, more efficient, but reading, of course, you need to load them from from the from the disk. Sometimes, 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 uh, if part of that program is loaded already in the memory, that means a shared library. If two programs are sharing the same library, some part of the instructions maybe are already loaded. I don't have to reload it. I can share that program, and we are going to talk about it at the end of this chapter. Organize question is swapping reflected to non-term words as bilgisayar kastı. I don't know what bilgisayar kastı means, but usually bilgisayar kastı happens. I hear people saying that when they load too many programs in their program and lots of swapping in and out is happening. Okay. Well, in my system, I have 70% memory occupied, so 30% is available. So whenever I need to load a new program, I have enough space to load it. Okay, let me try to load a Word file, maybe a large file. These are very small files. Maybe this one is large. So it is loading it. So as you see, okay, as you see that 75. So it is it loading it? What happened to Word? Word is not taking, I think Word is converting something to something. So I use 5% of my memory to load that thing, so I didn't have any problems. But if I don't have this 20% memory available, then I would have some bilgisayar kastı problems. But really, I mean, the definition of bilgisayar kastı maybe come later when we talk about trashing. Okay, trashing is the maybe better term for bilgisayar kastı. But I don't want you. Just go away. Go away. Okay, it's going away. Maybe. I don't know. No. So it has crashed. So it is restarting it. I don't want you to start. Okay. So it looks like bilgisayar kastı now. Okay, so let's move on. So how much memory should be allocated for a process? Of course, I mean, I need to load all the instructions. I need to load some data. Also, I need some space for data expansion, like the growing stacks and the heap size. So I need to allocate a little bit more space, like this one. For this program, okay, I have my program, my data, my stack space, and room for growth. So even though I am not using this space or this space, I have to keep it occupied in my memory. That's kind of inefficient. At the moment, I am not using that space, but I am occupying it. That looks like inefficient. Okay. With the swapping, all you are writing is you write your data and your stack out, right? You don't write this empty room. You don't write this program place. Okay. You only write this part and this part. Okay. So if I have more than one program in my memory, many programs, then I need to keep track of who is using what part of the memory. Okay. That's one part of the memory management. When the memory is assigned dynamically, the operating system must manage it. That means, in general terms, there are two ways of doing it. I mean, of course, you may come up with many other ways, but there are two general ways of doing it. One is bitmap, the other one is linked list. Okay, so let's say my memory is divided into, let's say, each part is 4 kilobytes, 4K, 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 4 and 4. So this process A needs 20 kilobytes of space, and this place is empty. 15 kilobytes of space is empty, and this one is 1, 2, 3, 4, 5. So this is 24 Ks. So I need to keep this information in a table. Okay, this is called part P, bitmap table. Okay, so for each 4Ks there is a bit available. So 1 means that place is occupied. 0 means that place is not occupied. So I keep using a single bit to indicate if a corresponding 4K chunk of memory is occupied or not. If I need to load a new program, let's say program G, if the program G needs 3 kilobytes, then this is a good enough place. So I put my program in there. And I would say this is G. Okay, I would make these three 1, 1, and 1. Okay, so Emre has a question. What happens for child processes if parent process is swapped? And swapping is not terminating, Emre. I mean, swapping is a swapped process is usually maybe a ready process or blocked process. It's not using the CPU. Okay, so the process itself does not know that it is swapped out. Like the process, I mean, no process knows that it is blocked. No process knows that it is waiting in the ready queue. Okay, they all think that they are using the CPU. So swapped out process thinks it the same way. It thinks that it is using the CPU. So nothing is affected. Remember, this is an abstraction method. Whatever we do with the memory management, the way program runs should not change at all. Okay? So swapping has no effect in regards to childs and that kind of stuff. Okay, if a program is terminated, of course, it is not swapped out, it is just terminated. It's just terminated. So this is what you do with the bitmaps. This is not the only way of, what is the advantage of bitmap? It is so fast. I mean, to understand if a location is occupied or not, okay, you would say that, let's say these are 4Ks. 4K means that each one is 2 to the 12, right? This is the size 2 to the 12. Let's say I have 2 to the 30 bytes of memory. So that means kilobyte, megabyte. This is 1 gigabyte, right? Is this 1 gigabyte? This 10 2 to the 10 is kilobyte, megabyte, gigabyte. Okay. So if I have 1 gigabyte of memory, and if my memory chunks are like 4Ks, that means that each one is this. So 30 minus 12 means that I have 2 to the 18. I have 2 to the 18 bits in my bitmap. 2 to the 18 bits means that if I divide it by 2 to the 3, 1 byte, okay, 2 to the 15. And 2 to the 15 is 2, 4, 8, 32 kilobytes. 32 kilobytes of data I need to keep this table. Okay, so that's not a very big table then in that case, right? Am I right? No. 2 to the 15, yeah, it's like that, yeah, 2 to the k. Yeah, so since each one is a bit, for 1 gigabyte, if each one is 4Ks, yeah, that's the calculation. Of course, if most of my memory is empty and if most of my memory is occupied, then this becomes kind of inefficient. In that case, maybe this representation is better. List representation. It says that from page number 0 to 5, it is occupied. There is a process. From, let me use this green arrows and okay, this one from 0 to 5, it is occupied. From 5 to 8, there is a hole, it is available. From 8 to 8 plus 6, 6 from 8 to 8 plus 6, it is occupied, etc. So this is the linked list representation of the available memory. Okay, somebody, Mehmet Hafif. Mehmet, this is your first comment, is not a question. You have a systems programming course at, okay. Let me give you a thumbs up for that one. Okay, so you have 2. So I think I am out of my time. Thank you, Mehmet, for reminding me that. And if you have a question, I can take the question right now. If not, I guess I will stop here, and next week I will start talking about the virtual memory and swapping again in more efficient way. Okay, I will be here for a little while more. If you have any questions, just ask me. Otherwise, thank you, and I will see you. Hussein, why did we divide 2 to the 3? Because this is a bitmap, okay? This is a bit. So if I get all of these together, 3, no. Okay, no. If I get all of these together, so this row is a byte, okay? So I am trying to make it calculate in terms of bytes, not bits. That's why I divide it by 2 to the 3. 2 to the 3 is 8. Okay, Hussein? Okay, if I don't have any other questions, that's it for today. I will see you on Monday then. And if you have any questions, just email me. Sir, can you upload these slides to the model? I mean, you asked this question many times, and I mentioned that these slides are already available in Moodle. Okay. All the pictures are available. Only my comments are not there, and these comments directly come from the book. Just read the book. Okay? Just open the book when you are watching my videos. Open the book, and these are word by word from the book. I don't add any new stuff from other places. Okay? If I add it, I give you my location like added with the table. No, slides are not different. I mean, the slides that I give you are from the book, and all the things that I am talking about here is from the book. I don't put any other material that does not come from the book. Everything is from the book. Okay? So don't study this course from the slides. Study it from the book. Slides are misleading. Okay, I'll see you Monday.